All right. So I'm thinking you'll need a calculator today. So kind of make sure you have a good calculator nearby. Okay. So we are going to start exponential and logarithmic equations in this chapter. So that button that says LOG on your calculators, or LN, we're actually going to be using those today. So you might take a second to look at your calculator and see if you can find those. Along with these will be used today. E to the X will be used today. Okay. So you should be able to see those somewhere on your calculators. All right. Okay. So what is an exponential function? Well, you can't come up with a better name. An exponential function is when x is in the exponent. Everything before now, x has never been in the exponent. X has always been down at the bottom. It's been the base. We've always had a number in the exponent, right? So whenever you have a number for the base and the x is in the exponent, that's what we call an exponential function, okay? Now, on top of that, we have some other restrictions to it too, you guys, okay? We want to make sure that the base, that this number down here in the bottom, is positive and not 1. The reason why we want it to be positive is because we're trying to get these two graphs out. We're trying to get what we call either exponential growth or what we call exponential decay. These are what exponential graphs look like, okay? Now, the problem with plugging in a number that's negative, let's think about this. If I put a negative number in my base, there's quite a few problems with it. Number one is, if I were to t-chart that, right? Whenever I raise it to the first power, it'll just stay the same. But when I raise it to the second power, a -2 times a -2, well, we know that a negative times a negative is a positive. Then if we raise it to the third power, right? Well, we know a negative times a negative is a positive, but then when you multiply that by another negative, it goes back to negative again. And by the way, the next one would be positive. So your graph isn't going to be that pretty graph that we want. It's going to be like, okay, at 1, I'm down here at -2. At 2, I might be like up here at 4. At 3, I'm going to be back down here at negative. At 4, I'm going to be up here. So you get these dots that are just going to keep ping-ponging, you know, below, above the x-axis. And it gets worse. I should be able to t-chart a half. But what the heck does it mean to raise this to the half power, you guys? Well,
divided by 2?
Close, good guess. It's kind of almost like that. It means square rooting it. Remember, the bottom is the root. We kind of talked about that a long time ago. So this would be the square root of -2. Well, that's imaginary, which means I'm not even going to get a value out when I plug a half in. So here's a half on the number line, and it's like, I'm not able to get a value out for that. So it'll be empty there. And many other values would be really hard to get. You know, anything like 3/2, same deal. 3/2 means that it's going to be square rooted, and then it's going to be cubed. So remember, the bottom's the root, and the top is the exponent. So again, imaginary, you guys. Okay. So These are both going to be imaginary, which means we don't get a value out, which means our graph is disconnected. Boy, this is hideous, right? I have all these dots, and that's it, guys. Okay. So this is bad, very bad. Bad to have a negative in there. Bad to have a negative. We practice this, but I feel like we need to come back and practice it right now. Let's do these really quickly, you guys. I want you to be so good that when you go to calculus, you just do them in your head. Okay. What does the top one mean that we have? What root?
Root of cubic root.
Cube root. Good. And then you square it. So what is the cubed root of 8?
2.
Good. And then 2 squared gets us 4. All right, what does this one on the bottom mean? The what root?
Quadratic.
So square root. And then the top is the exponent. So if we square root 16, we get 4. And then 4 times 4 times 4 is 64. So it's always the bottom that's the root, you guys, okay? All right, that was just a reminder, blast from the past. All right, so bad to have the negative, very bad. But why not 1? Because it does say B has to be positive, but then it says B can't be 1. So it's like, what's up with that? You know, why can't B be 1? Well, how boring is this? I mean, if we have f of x is 1 to the x power, it's an exponential, that means x is in the exponent. Well, I mean, nothing exciting here. Plug in a bunch of values, right? Okay, so what is 1 to the first power?
1.
What about 1 squared?
1.
1 times 1 is 1, huh? Okay, 1 cubed?
Also 1.
1 times 1 times 1 is still gonna be, it doesn't matter how many 1s I have there, 1 times 1 times 1 times 1, still 1. So this is really boring, yawner, right? Here's 1, da, 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 right? So this is just utterly boring, okay? So they've excluded 1 because it's boring as heck, and they've excluded negatives because then we won't even get answers out in our t-chart because we'll have imaginaries and stuff. And we won't get these pretty graphs that we want right here. So exponential growth and decay means very quick growth or very quick decay. In English, people say, man, it grew exponentially. And when they say something grew exponentially, they mean it grew fast, okay? Because here it is, and then it just shoots up really fast. Okay, it's not like a line. Most lines are very slow growth, right? It's like, I'm just gonna troop along, I'm gonna grow eventually, right? This is like, up to infinity fast, okay? Same thing is true for decay. It's not gonna decay, the decay is gonna decay fast, and then it kind of tapers off and decays slowly, okay? But that initial decay is so quickly, okay? All right. Okay, so let's t-chart some of these, you guys, and see what happens. You know, we know what we should get. Okay. Was there anything else that I wanted to tell you though that no, it hasn't told us yet? Okay. Okay, so because I want you to get good at raising to various powers, I'm going to force you to pick some negatives and some positives. Okay. All right, let's start there. So what does 3 to the negative second power mean? How do I rewrite that? What the heck does a negative exponent do? Okay, forgotten. Nope. Nobody knows? Usually I have one person that knows. Nobody remembers?
Well, isn't it gonna be 1/3?
Yeah, to the positive second now?
Uh-huh.
I think you just jogged a lot of people's memories right now. Okay, yeah, we kind of talked about that. You're just rare enough to forget, but now that you see that, is everybody like, oh yeah, put it under 1 or flip it or whatever your teacher said. Okay. So that's going to be 1/3 times 3. So that's going to be 1/9. Okay, let's do it again, but we're going to raise it to the negative first this time. So again, 1/3 to the positive first. So that's just 1/3. Okay, our next hurdle, anything to the 0 power. Is it 0 or is it 1? Anything
1.
1, good. Everybody wants to put 0 for that one. Yep, so it's going to be 1. All right, these everybody's good with. 3 to the first, well, 3. 3 to the second, 3 times 3 is 9. And what about 3 times 3 times 3?
27.
7? Okay. We're going to go off our graph past that, so we'll stop there. Okay, let me see what's going on with that. Okay, my volume's on. Can you hear me now, you guys? Okay, now it's better? Interesting. Okay, so let me go back, just kind of see where I lost y'all. So what I was just saying is make sure that you don't cross the x-axis. This is an asymptote, so you want to show that you're getting close to it, but that you're never crossing it. So let me undo the graph. Sorry, I gotta go back. Oh, darn it. You know what? I will just erase this then. Guess I'll just have to do it by hand right here. All right. Put these back, you guys. Okay. So in other words, what I want to see is that you go like this. And this is really subtle, but I didn't cross it. I just show that I'm going to get really, really close to it. Think about this. If it never crosses it, then that means that this can never be 0. You know, and you can try all day to see if you could get 0 out of that. But it's like, okay, when we plug in negatives, it just makes it a fraction. When we plug in 0, we get 1. When we plug in positives, it's just going to be a positive number. So no way are we ever going to be able to get 0 or a negative out. And that's what you're seeing here. No negative numbers, not even 0, because I'm just going to get really close, but not touch. Okay, so keep that in mind when you're graphing these, you guys. The x-axis will never be touched across, so it's an asymptote. Okay, so what would we call this? This type of a graph. This would be exponential what, you guys?
Growth?
Yeah, super fast growth. There we go. Now, it turns out that as long as this number that's your base is bigger than 1, it should grow. Let me see if they have that written down somewhere. They do right here. Okay, let me kind of talk about it right now. So I was teaching at Sultana High School, and one of my students called me over. They said, Mecklenburg, my calculator's broken. And I knew which section we were on, so I kind of already knew, what was going on. So they had put some number like 0.67 into the calculator, and they squared it. And when they put that into the calculator, let me go ahead and get 0.67 squared, you guys. It becomes 0.4489. And so the student was saying, hey, my calculator's broken. And I was like, well, why is your calculator broken? And they said, well, I squared this, but it got smaller. And I could totally see how they were thinking that, right? Like most of the time when we square things, right? What happens to them? They get bigger. Whoa, let me write that better. Most of the time they get bigger, right? Okay. So it turns out that's not always the case though. A really easy example to see is what if you squared a half? If you squared a half, wouldn't it become a fourth? And definitely 1.25, right, is smaller than 0.5. So it turns out that when we square some numbers, they get smaller. The question I want to ask you is, when do we square numbers and they get bigger? And when do we square numbers and they get smaller? Okay, so what numbers grow when you square them? That's going to be the first question. I'll say this, what numbers decay? Square them. You guys have any guesses?
If the numbers are bigger than 1.
Yeah. So bigger than 1, I love how you said that too. You didn't say greater than or equal to 1. You said bigger than 1. Because 1, when you square it, it doesn't grow. So we can't put that on the list. That's why we don't have the or equal to on it. Okay. All right. Now I want to think about what numbers decay when you square them. So what do you guys think? What kind of numbers will shrink when you square them?
Anything that is less than 1?
Yeah, and I have some students say fractions, which is a good guess. But here's a fraction, 3/2, which is 1.5 in your calculator. When you square that, you get 9/4, which if you put that into your calculator is 2.25. So this fraction actually grew. So it's not all fractions that shrink, but you nailed it. It's ones that are less than 1. So I don't want the top to be bigger than the bottom, you guys. I want the bottom to be bigger than the top. So something like 2/3, that should work. 2/3 is 0.67-ish. When you square it, it becomes 4/9. It should be smaller. Let me see what my calculator says for 4 divided by 9. It's giving me 0.44, so it did shrink. Cool. Now, they also make sure it's bigger than 0, because remember, we're not allowed to have negatives, you guys. And we're not allowed to have 1. So that's all kind of stated right here on this page. It says, maybe it's not stated. think it's going to be stated eventually though. But so where this will be growth if b is greater than 1, and this will be decay. And you guys just saw that. You had a 3. 3 is bigger than 1. So when I square it, it grows. And look at this graph. We have exponential growth going on. Okay. All right. Let's try this one. So before you do one like this, you guys, I recommend you rewrite it. What I mean by that is exactly what we just did a second ago. Let me pick your guys' brains and see if you can tell me how to rewrite that. 2 to the negative x.
1/2.
1/2 to the positive x?
Yeah.
Okay, cool. And I can rewrite it even further. This is how we typically would rewrite it, is we'd go, okay, let's rewrite it like that then. So let's think about why it's legal to do that. When you have an exponent on the outside of a fraction, it actually goes to both. It goes to both. For example, if I have 1/2 squared, doesn't the 1 get squared and the 2 get squared? And that's why we ended up with 1/4, you guys. Okay. But 1 to the x power, we said 1 to any power on the face of the planet is just going to be 1. And so that's why I'm allowed to kind of put it on the x. Okay. Now that's just, you don't have to do this. I just wanted to point out that this might happen on Connect Math. They might have you rewrite it in the following way. Okay. And what's the benefit to rewriting it like this? You're like, Mecklenburg, why? It would have been easy to just do it right here. Well, the reason why is now just by staring at it, you can tell me if it's going to be growth or decay. So is this going to be growth or decay for this one?
Decay.
Yes, decay, since b is greater than 0 but less than 1. Remember, it's always b to the x power, you guys. So b is the base, b for the base. Okay. All right. Now, you can use either one of these to t-chart it. I don't care which one you guys use. Okay. So let's go ahead and come in here. And again, I want to make you guys pick some values like -2, -1, 0, 1, 2. Okay, yes. I probably should have picked, you know what? Let me undo that. Sorry for people who are writing their notes. Let me do this and we'll see why in a second. Okay. All right, let's go through the math together. Okay, so -3 as an exponent. Ooh, another challenge for you guys. Do you remember what to do when you have a fraction raised to a negative? A fraction raised to a negative.
So this
I don't know
one,
why I think we should switch them.
So now it's just
Yeah.
moving with an
You do.
initial
You flip it.
velocity.
You flip it, and then you make it a +3. So 2/1 is just 2. So this is really 2 to the 3rd. So 2 times 2 times 2. So 2 times 2 is 4. 4 times 2 is 8. So this is going to be 8. So what this is telling me, you guys, is we're probably using our calculator like too much. Like we're dependent on it. You know what I mean? Like as soon as I give you something like this, you're not even thinking about how to do it by hand. You're just thinking, let me plug it in the calculator, right? And that should be plan B. You know, you always want to try to do by hand what you can. Heaven forbid, you know, some technological collapse happens and nobody knows how to do any of this stuff, right? They're like, well, I don't know, my calculator just gave me the answer, right? But on top of that, it's actually faster a lot of times to do these things in your head, because by the time that you've wrapped parentheses around the 1/2, or I bet some of you might even get it wrong, because like some of the calculators, if you hit 1 divided by 2 and to the -3rd power, You know, without the parentheses, it's only going to do it to the 2. You know, so some of you would probably even type it in wrong. So you do want to make sure that you're quizzing yourself. Am I dependent? Like I need this calculator, or is it just a, you know, a tool to help me think, right? So don't let it replace the thinking and do it for you. You got to try to do some of this stuff by hand here. Okay. So a fraction raised to a negative, flip it and raise it to a positive now. So 2 times 2, 4. A fraction raised to a negative, flip it. Instead of 1 over 2, 2 over 1, which is just 2. Now it's a positive. How quickly we're blazing through. All right, you guys should pass this check. Anything to the 0 power?
1.
Yes, 1, done. And now it's the easy stuff. Anything to the first power stays the same. 1/2 to the second power just means 1/2 times 1/2. 1 times 1, 2 times 2. And 1/2 to the third power would just mean 1/2 times 1/2 times 1/2. So 1 times 1 times 1 is 1, and 2 times 2 times 2 is 8. There we go. Okay. So we already know what the shape of this should look like. You guys said decay. You are on it, decay. So we know we should get something where it's like da 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 da. Nobody's going to cross the x-axis. We already said that. Okay. All right, let's see here. Negative 3, 8. Negative 2, 4. Negative 1, 2. 0, 1. 1 1/2. 2 1/4. 3 1/8. Oh my gosh, it's getting so small I can't even grab it now. All right. So we're going to go ahead and make sure that we don't cross the x-axis on it. So you bet that is exponential decay. Okay. Are any questions on that, you guys? So fraction raised to a negative, flip it and make it a positive. Flip it and make it a positive. Okay. All right. So for this one, let's go ahead and take a look at it really quickly. I think I would just T-chart it. That's what I would do. Yeah, let's just T-chart it. Okay. All right, let's pick some negatives. And let's pick some positives. All right. Okay. Just to let you have you guys realize, you know, how important these are. We're going to have a lot of word problems that are going to use exponential. Okay. The applications for this are everywhere. Okay. So one of the applications is carbon dating, any sort of radioactive element and its half-life. So that's how they age stuff, is they know the half-life for these radioactive elements. So they know how much they should expect to be present depending on a certain age. So we are going to do some carbon dating problems, okay? Another for nurses, the half-lives of medicines are often used. Let's say when somebody comes into the emergency room, one of the first things you ask them is, have you had any medications and how long ago did you take it? And so what they can do is they can, based off how that person responds, they can know how much of that medication is still in their system because they know the half-life of each one of those medicines, okay? And they follow an exponential decay model. The amount of it present in your blood will decrease very quickly at first, and then will kind of slowly decrease after it, kind of like this guy right here, okay? Also, population growth. So if you look at the population of the world, if you look at graphs of it, for example, so let's say now we did have some, you know, notable times of deaths, but even what seems like the huge catastrophe are little blips in the grand scheme of things, like plagues, wars, you know, stuff like that. And so you'll notice, check this out, you guys. I mean, come on. This is perfect exponential growth, right? So populations at the beginning, they kind of start off growing slow, but then after a while, boom, they just kind of take off. That is crazy how good that looks as an exponential model. Okay, so the applications for these, man, they're just off the charts. If you get a chance to take all the way up to differential equations, you can see a lot of applications. Oh, hey, here's an application of it. Disease spread. So all those, this is how many people are going to die from COVID that they gave us a little while ago. Those are based off exponential models. Like if I'm in contact with, you know, 2 people and then those 2 people are in contact with 2 people, you know, and stuff like that. All that's based off exponential models so that they can kind of guess as to how many people are going to get infected. So epidemiologists, people who study diseases, use these exponential models quite a bit. Okay. So this is a big section. For some reason, when students get out of 105 and they're in my Calc 1 class, this chapter they've just dropped out of their brain, and I think, oh my gosh, logs and exponentials are what you're going to continue to use from every math and from then on. So this is important, is what I want you guys to get out of it. Okay. All right. So let's go ahead and continue on, and we are going to do a whole section of just word problems. I can't remember what section it is. Maybe it's like 4 or 5 or something. But so you'll see just how important it is. Okay. So we are going to go ahead and do the math here. So we're going to substitute in -3 and see what happens. So -3 plus 1 is going to get us -2. And we just got done saying that raising that to the -2 power means really 1/2 to the +2 power. So this is just 1 minus 1/4, which you can use your calculator or you can just kind of do it by hand, whatever, 3/4. Okay. All right, let's plug in -2. All right, 1 minus 2. -2 plus 1 is -1. We just said if you have a negative exponent, put it under 1 and make it a positive exponent. So this is going to be 1 minus 1/2, which is just half. Now we're going to plug in -1. -1 plus 1. Well, negative plus 1, that's 0. Anything to the 0 power is 1. 1 minus 1, 0. Now we're going to substitute in 0. All the hard parts done with, you guys. 0 plus 1 is just 1. 2 to the first power is just 2. And 1 minus 2 is -1. We'll plug in 1. So 1 plus 1, that's going to get you 2. 2 squared is 4. 1 minus 4 is -3. All right, let's see if this is enough for us to get the graph going, okay? -3 up 3/4. -2 up 1/2. -1, 0. 0, -1. And 1, -3. Okay. I think we can kind of see what's going on. Maybe. Kind of looks to me like it's doing this. It looks like there's a horizontal asymptote to me at 1. Okay. Horizontal asymptote at 1. So I want to make sure I don't touch 1. that I get really, really close to it. Okay. So if you can't see, plug in more points. Plug in -4, plug in -5, and see what happens to it. Here's a little hint. You have your exponential part, right? The part with the exponent. This other part is your horizontal asymptote. So if I gave to you guys, 3 to the x minus 7, right away I know -7, 1, 2, 3, 4, 5, 6, 7, is where I would have my horizontal asymptote. Okay? So that back number is going to be the horizontal asymptote. You might not be in the back, but the number that doesn't have the exponent. So in our case, the 1 would be where the horizontal asymptote would be. There we go. Okay. All right. Okay, so that button on your calculator, the E button, right? What the heck is E? So let's talk about that. You guys know what pi is. You've been looking at pi, maybe elementary, junior high. But pi is what we call an irrational number because it's a number that goes on forever. 3.14157, blah, 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 goes on and never stops, right? And it cannot be turned into a fraction. So this is pi. This is the only irrational number really that you guys know at this point. We're going to add another famous one today. So E, just like pi, is another irrational number. It's about 2.7 something. Okay, oh, it has it up here. They should have dots because this goes on forever. So what I want you guys to do is find the E to the X button on your calculator and see if you can give me E to the first. And it should give you this as a value. So take a second, see if you can find that on your calculator. And if not, if it's not giving you 2.7, let me know because I can just Google your calculator and show you what buttons to push. So type E to the first in and see if you get 2.7. Okay, Karen's got a yes. Does anyone have a no? And I can Google your calculator. Shai's got it. Okay, cool. If you're using an iPhone, it kind of sucks because you got to hit the 1 first and then hit the E to the X button. It's kind of backwards if you're using your iPhone calculator. And I want to say some calculators are that way too. So if you're not getting it, try 1 first and then hit it. This is a first. Everybody seriously getting it? Because usually when I have face-to-face, I have a good 5 or 6 people that aren't getting it on their calculator. Everyone's good? Okay. All right, because I have a bunch of things for you to do. So you're going to plug in this entire page right now, problems 4 through 7, into your calculator. And I want you guys to get round to 4 decimal places. So give me 4 decimal digits for each one of these. Let me give you about a minute to get that going and write it on a piece of paper, and then we'll see if we match, okay? Okay, so I'm matching with Karen on the first one. And let's see if we can follow the directions and give 4 decimal places. So 1, 2, 3, 4. So it looks like the 5 is going to round that 0 up to a 1. Let me put an approximately symbol to be exact here. So that'd be the answer for the first one. All right, what kinds of things are we getting for the second one, you guys? All right, let me see if somebody else gets that. Usually if two people get the same number, I trust it, because it's no way you guys are gonna get just the wrong answer in common, you know? Is anybody else getting 0.0498? Michael's got it, okay. And then 0.04978 is what I think it was, right? So if we do 4 decimal places, 1, 2, 3, 4, Karen already rounded that 7 up to an 8 for us. All right, so 0.0498. All right, e to the square root of 7. E to the square root of 7. Okay. Okay, Giovanna, Karen, you guys match. So I'm thinking that that is the answer there. Oops, I forgot my approximately sign. I keep putting equals. Approximately. Okay, so 14, yes. 0.0940. What was after that, you guys? Just so we can make sure we rounded right, a 3? Okay, cool. All right, so yeah, if you do 1, 2, 3, 4 digits, 3 will not round the 0 up, huh? Since it's less than 5. So that's why they kept it a 0. Good call, you guys. Nice. Okay, and our last one would be e raised to the pi. So you also have to find the pi button on your calculator. Okay, you guys are getting it. So 23.140. What was after the 0? 69. Okay. So if we have 4 decimal digits, 1, 2, 3, 4, 9 rounded the 6 up to a 7. You guys were right. Good job. Nice rounding too. So 23.1407. Excellent. So if some of these come up on the homework, which they will, it sounds like you guys got a handle on it. Okay, so great work there. Let me make that 6 look a little better. Okay. All right. So we discovered a new button on our calculator, the E button, right? Okay. All right. I will do this last one, you guys, and then we'll go ahead and take a break. But we are going to need our calculators for this because E is so ugly, right? It's like that 2.7 blah, 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 blah. So we're not doing this by hand, no way. So here we go. Let's get a couple negatives for good measure. All right. Now, before we start, ooh, tough question. Growth or decay? What are you guys thinking?
Isn't it gonna be a growth?
It is.
Because
Good.
the constant is 2. So
Yeah.
it starts with a 2.
Yep. So it's growth. Remember, E is around about 2.7. So since the base is greater than 1, growth. Any number greater than 1, when you square it, it grows. So if you took 2.7 and you squared it, it would get bigger. Okay. All right. So we are going to, I'll just do it in here. It looks like I have enough room. So we're going to plug in -2. We're going to plug in -1. Plug in 0. 1, 2, 3. All right. So this will just be e to the -1. This will be e to the 0. Oh, we can do that one by hand. What's e to the 0?
So we don't have
Good.
Which is 1.
Yep. 0 power is 1. Nice, you guys. Ooh, we could do this one by hand too, because this just is e to the first, which means it's just e. So 2.7-ish. All right. And then the rest of these, we will have our calculator do for us, just because they're so gnarly. Okay. All right, so let's start off with e to the negative 1, you guys. So go ahead and put e to the negative 1 in your calculator. Let's see what y'all are getting. Just give me 2 decimal digits. That'll do it. Because we got to graph these things. No one's going to be able to tell the difference between 0.3 and 0.4, huh? Okay, I got a 2.72. Okay, so just make sure you wrap the negative 1 in parentheses, you guys. If you hit e caret parentheses negative 1, just to make sure. I think you forgot the negative on it, actually, Karen, huh? So try that one more time. What kind of answers is everybody else getting? .36? Yeah, 0.37, 0.36. Okay. Good. Awesome. Okay, e squared. We're on this one right here, you guys. E to the second. $7.39 from Karen. Did anyone else get 7.39? Cool. Shai got it? Okay. All right, let's go on to e to the third. E to the third. $20.09. That's right. We're getting pretty big, huh? That's not even going to fit on our graph anymore, you guys. So I don't even think we need to do this last one. If Karen's right on that, did anybody else get 20.09? Let me give it a little bit more time. E to the third. Okay, Jocelyn got a yes. Okay, all right. So we probably won't graph that one. Dom got a yes. Okay, we probably won't graph that one just because it's so big, you guys. So here we go. -2, -2.37. All right, so remember 1 is right here. So when somebody says 0.37, man, you're not even 1, huh? So maybe really, really small. All right, the next ordered pair, -1, 1. So -1, 1. 0, 2.7. So if 3 is right here, 2.7 would be less than 3, so maybe like right there. All right, 1, 7.39. So 1, 7's right here. So 7.39 would be higher. And that's all we got. Okay. The back number is 0. There's a +0 on the back end that's not there because why write it? Which means that's the horizontal asymptote again, right? 0. So don't cross 0, you guys. There we go. You were right. You guys said growth. Indeed, it is exponential growth. So good call on that. All right. Okay. Let's go ahead and take a break there. Let's see here. It is 4. Oh, perfect, you guys. All right. So meet me back here at 4:10. All right, let's talk about how to make you guys some money, okay? Loosely. So I totally forgot that this is one of the applications too. So interest. So we're gonna have formulas for compound interest and for continuously compounded interest. Simple interest you might have seen before in a previous class maybe, but these are going to be the two that we're going to use here. So if somebody says, you have compound interest, make sure you use this formula. If somebody says continuously compounded, then you're going to use the bottom one. So the important words are just compound versus continuously compounded, okay? I'm going to go over each piece in the formula so that you guys understand what everything stands for, okay? So A is always going to be the amount in the account after T years, okay? So A equals the amount in account after T years, okay? P stands for the principal. Does anybody know what that means, the principal? I'm assuming it's a new word for a lot of people. All right, so nobody knows what the principal is? Okay. So the principal is the original amount either borrowed or invested. So when you have like your house loan, right? If you overpay, then that whatever you paid over for the month, it goes to your principal. So what that means is it's going to go towards the original amount you borrowed. So let's say I'm supposed to pay $1,200 a month for my mortgage. In 1 month I have extra money, so I pay $2,000. That extra $800 will go all towards the principal. It's not going to go towards the interest, which means it's just going to bring down that original amount that you borrowed. Okay. Now it could be the other way around. It could be I'm investing. So instead of borrowing, like maybe I went and invested, a certain amount into an account that gets compound interest. Okay. So the original amount borrowed or invested. The R is going to be the rate as a decimal, not a percent. T is always going to be in years, time in years. So don't give me months. If somebody says you invested it for 3 months, then you better not put 3. Okay, you better put 3 out of the 12 possible months, which gets you a quarter of a year. Okay, so make sure that you're always giving it to me in terms of years. That's something I could see myself doing. It says 3 months and I just go and put a 3. Okay, so we always want it in months. In years, sorry. And then what am I missing? The new thing that probably we don't know also is N, which is the number of compoundings per year. Number of compoundings per year. Okay. So they might say, okay, it was compounded monthly. If it's compounded monthly, then that would be 12 times per year. They might say compounded quarterly. Well, if they compound it once every quarter, then that'd be 4 times a year. Or they could say compounded daily. If it were compounded daily, you guys, how many times per year would that be?
Five.
Yep, 365. Yeah. Okay. Since there's 365 days in a year. All right. So let's go in here and see. With this problem right here, you're going to see that the more frequently it's compounded, the more money that you'll make or the more money that you'll owe depending on the scenario, okay? So it says here, suppose that $15,000 is invested with 2.5% interest under the following compounding options. Determine the amount in the account at the end of 7 years for each option. So let's go in here. We have our formula, right? This one right here. we're going to need to figure out what each letter is. Okay, let me make sure I wrote it down right. Yeah, okay. All right. So read through the problem. See if you can tell me, you know, maybe what P is, maybe what R is, what T is, and what N is. Do we know any of those, you guys?
We know R.
R,
The
okay.
rate is 2.5, right?
Good. So if it's 2.5%, we got to move that decimal place twice to get the decimal. So our R is going to be 0.025. Okay, good. We got the R. Shai is saying T would be 7, and it's already in years, so we can just keep it. Cool. So is the 15,000 the original amount borrowed or invested, or is the 15,000 the amount in the account after 7 years?
No, the original.
Okay, so then that's going to be our P, because P is always the original. All right. Now, if it's compounded annually, then how many times is it compounded per year? It's a weird question, I know.
1.
Yeah, 1. Okay. So if it's compounded annually, it's only compounded once per year. So n equals 1. Okay. Okay. So now it's just a matter of plugging in and using our calculators correctly. So let's see here. If you have a good calculator, it's helpful in this section. So 15,000 is going to go where the P is. The rate is 0.025. You gotta divide that guy by 1. And then the N is 1 times the T. Now I like to clean up what I can before I go to my calculator. For example, dividing by 1 doesn't do anything. So I would just leave this guy as 0.025. Also 1 times 7, why not do it? 1 times 7, 7. So go ahead and plug this into your calculator, you guys, and we'll see what the amount in the account is after 7 years. See how much money we make here. When you get it, just type it into the chat. Thanks. We got 1 in there. See if we got some matches on that. All right, is anybody else getting 17,830-ish? Dominic's got a yes on that. Okay. All right, now, since it's money that we're talking about, I think we know where to round. So since it's money, we want to round to the nearest cent, right? So we're going to go ahead and say, let me type that out just to remind everybody. Okay. So since it's, don't round to the nearest dollar, round to the nearest cent. Okay. Because you know your bank's going to be doing rounded to the nearest cent. Okay. All right. They're not going to round up for you. It's 75 cents. They're not going to make that a full dollar amount. Imagine how much money they would give away if they did that for every account, right? Okay. So we're going to go ahead and say that the 6 is going to round the 8 up into a 9. So this is how much money would be in the account after 7 years if we only compounded it once per year? Okay. Any questions on that, you guys? Okay, let's try another one. So we're going to up the number of compoundings, you guys. We are going to compound quarterly. Same scenario. Same scenario. So the principal, the original amount was still $15,000. The rate is still the same. It's going to be that 0.025. Don't forget to always move the decimal place twice. The time will be 7 years. But we're going to compound it quarterly. So what would be the number of compoundings per year? Okay. Good guess. Think about high school. When you were in high school, you guys, how many quarters were in the school year?
4. Is it 4?
4, right? Yeah, okay. So quarterly means that it'd be 4 times per year. You go and you quickly hide your report card. I'm just kidding. All right, so if compounded quarterly, then there would be 4 compoundings per year. Okay, so in other words, n is going to be 4, you guys. Okay, so we have that same formula. So we still invested 15,000. We still have a rate of 0.025, but this time we're compounding it 4 times per year. All right, probably would be easiest to make that exponent a 28 and then go to your calculators. So let's see what the amount in the account's going to be. Hopefully it's higher. We upped the number of compounding, so we should have made a little bit more money. I'm going to put the answer down. I want you guys to make sure you're all getting it. And if not, just ask me and I'll tell you how to put it in on your specific calculator, okay? Okay. So make sure that you're getting that. You guys are pretty quiet today. Okay, Carlos has a yes on it. Anybody not getting that? Because this one's tougher to put in for sure with that 0.25 being divided by 4. Is there anyone who's not getting that answer? Okay. All right. I think some of you are lying to me, and you're being shy, but okay. All right. So the people that are quiet are just like, I'm not going to say. All right, let's see. So it's money. So we're going to go ahead and make it 96 cents. And how does that stack up to last time? Let's see. Last time we made $8.30. This time it's $8. So 28 bucks more. Nothing changed except for the number of compoundings was 4 times per year instead of once per year. We got an extra 28 bucks. I'll take it. Okay. Now this next one is going to up the number of compoundings to infinity. That's what it means when somebody says compounded continuously. That's not even daily. Daily was 365. Continuously means we let the number of compoundings per year go to infinity. And in Calc 2, we actually proved the formula. We just did that the other day in my Calc 2 class. So This means the number of compoundings per year is actually infinity. If you were wondering what the heck compounded continuously meant. Okay, so, all right. So we should expect even more because man, we went from once per year to 4 times per year, and now we're saying infinity times per year. So it will be a little bit higher, nothing super, super major, but a little bit higher. Let me kind of talk about why it gets bigger and bigger, okay? If I compound just once per year, let's say I start off with $2,000. Let's say the interest rate is 10%, okay? Well, 10% of that would be 200. So now if you put these two together, now there's 2,200 in the account. And I'm going to do 10% of that. So I'm going to be getting interest, not just on the original amount now, but interest on the interest also. So I'll be doing 10% of 2,200. Well, now it'll be 220. You add the 220 back to the original. Let me see, 2200 plus 220. Now we have this much in the account. So this is how compound interest works. Compound interest means you're getting interest on your interest. So you can see why you would want to have more compoundings per year, because what they're doing there is they're going to say, okay, you got this interest, add it back. Now we'll do interest on that. Oh, you got this interest, add it in. Now we'll do interest on that. And so it makes it grow a lot faster, okay? Because you're getting interest on the interest, if that makes sense. Okay, that's what compound interest is all about. It's interest on the interest. Okay. So compound interest grows pretty quickly. All right, let's see here. Now remember we said if you see the word continuously, that means it's a whole new formula. Okay, that means you're using this guy, who's much easier, by the way, PERT. Good old PERT. Now E is not a variable. So I'm not going to write him over here and say, okay, well, what's E? No, E's a number, right? It's 2.7, so I'm not going to write him down. The only things that we need to find are P, R, and T, okay? Now we already know the principal is 15,000. We already know the rate is 0.025. We already know the number of years is 7, okay? So we are going to plug all of that in to the formula. Just leave E as E. Maybe we'll just hit times. No, maybe I will do it that way. Okay. So if you're bad with the exponents, then you might as well just do 7 times 0.025 right now. My calculator is giving me 0.175. That's a little bit easier to type in. So again, you guys got to locate that E button. So take a second, substitute this in, and let's see what y'all get. Hopefully it's like 17,000 something. Let's see. Okay, so Karen, that sounds reasonable. I mean, it's close to what we were getting for the other ones. Okay, cool. So since it is money, we are going to round to the nearest cent. I don't know why a 3 came out. So it'll be 0.69. Now that should be more than when we only did it 4 times per year. Let's go see. Yeah, we got an extra 10 bucks, you guys. It was $58 for that. Now it's $68, right? So we got an extra 10 bucks off having it continuously compounded. So if you're trying to make money, look for continuously compounded. If you're borrowing money, then you don't want continuously compounded, right? I guess it just depends on the scenario, you know? All right. Okay. So those were some applications. Let's look at some others. So this is what I was talking about with the radioactive decay. So we have a lot of radioactive elements, right? And this one, it says weapon grade plutonium is composed of approximately 93% plutonium-239. So there's your radioactive element right there. Okay. The half-life of plutonium-239 is 24,000 years. Now, these half-lives are documented. Like if you Google half-lives for radioactive elements, it'll tell you, you know, the half-lives for them. So let's see. Half-life for radioactive elements. Now they're rounding, by the way. They're never exactly what it says in these word problems. But let's see here. Maybe it was the next one that I wanted. Okay, so here's some. So you got hydrogen 7, hydrogen 5. I forgot what we had. Plutonium 239, was it? Yeah, plutonium 239. Let's see if it's on the list. Oh, this is half-lives of seconds. That's not going to be on the list. These were long half-lives, right? I don't see it, you guys, but I'm sure I could Google it. Okay, so it's really 24,100. I think they just rounded it to like 24,000. Yeah, not our problem. Okay. So let's talk about what that means, right? What the heck does a half-life mean? So let's say that you have a medication. Now let's just say something, whatever it is, has a half-life of 2 years. Now let's make it 3 years, just so we don't have too many twos. And let's say that it starts off with 20 grams of whatever this element is. So that means that when time is 0, you got 20 grams. Now let's say 3 years have passed. Then that means now I'll have half of it left. I'll have 10 left. If another 3 years pass, so now it's been 6 years, I'll half it again. Another 3 years pass, I'll half it again. Okay? So when somebody says something has a half-life of 3 years, then that means it'll decay to being half as much if 3 years pass. So for these radioactive elements here, like this plutonium-239, right, that has a massive half-life, that's how we date really old things. Things that go way back in time, right? You don't want to pick something with a short half-life. If you're a nurse, those medications have very short half-lives, okay? But if I'm trying to age something old, then I want a large half-life or something. Okay. So once every 24,000 years, or once 24,000 years pass, half as much will be present. That is what half-life means. So I claim we could get these just by understanding what half-life means. So it says the original sample contains 0.5 kilograms. That's the original amount. Okay. So if I were to make a chart out of this, right? Time and amount. We know that when time is 0, aka the beginning, we have 0.5 kilograms. Now, if the half-life passes, so 24,000 years pass, well then I should half that. So I should have 0.25 left. Okay, and that'd be kilograms. Now, if another 24 years pass, 24,000 years, then I'm at 48,000 and I'd half that again. Then if another 24,000 years pass, so 48,000 plus 24,000, that is, whoa, what do you know? 72,000, you guys. And I got to take 0.125 and divide that guy by 2. This is how much would be present. How many kilograms should be present if that many years passed? Okay. All right. Now, that's one way of doing it, and I think that's the easier way. I was just thinking logically about it. But we could do it besides this. We could actually plug these numbers in. So those of you who really like formulas and stuff, okay, you're just going to take the t and you're going to plug it in right there. So this would be 0.5, 1/2, and then you'd put 24,000 on top of 24,000 according to the formula. So that means it'd just be 0.5 times 1/2 to the first power. So if I do 0.5 times 1/2 in my calculator, guess what? It's 0.25. Similarly, plug 72,000 in for the t. So you have your formula, 0.5, 1/2, take the 72,000 and put it in for the t. So 72000 divided by 24000. Sorry, that's hideous. Let me see if I can write that better. Goodness, sorry guys. Okay, so that's 0.5, 1/2 to the third. If you put that into your calculator, 72,000 divided by 24,000. Yeah. And let me go ahead and plug this in. 0.5 times 1 divided by 2 to the third power. Yep, there it is. 0.0625 kilograms. Again, I kind of prefer just thinking about it logically because the meaning is lost. You just use this formula, right? You don't understand what half-life means. This shows that you understand what half-life means. Okay, I think taking that away from this class is going to be important. All right. In 2010, an estimate of the population of Mexico is 111 million people with a projected growth rate of 0.994% per year. At this rate, the population in millions can be approximated by that formula where T is the time in years since 2010. Ooh, we just had the 2020 census. We should go check and see how right it is. Let's see. Okay. Let me change this from 75 to 10. So that way we can check the census. I don't know if they have their census results out yet, but let's look for it anyways. Okay. All right. So P of 4. Okay, take 4, plug it in. Let's see what we get. So we got to do 111 times this guy. Boy, this is gnarly, huh? To the 4th power. All righty. Calculator time. 111, 1.00994 to the 4th. Okay, this is what I'm getting. It doesn't say where to round it, huh? Okay. I'm getting approximately that, you guys. Yeah, okay, cool. All right. So interpret the meaning in the context of this problem. All right. So you know what I want to do? Because here's my dilemma. I don't know if they just want you to round it and say there were approximately, 115 million people in Mexico. I mean, that's a lot to be rounding, in my opinion. So I want to go consult your Connect Math just to make sure I do it the same way. Because it doesn't tell us where to round, you guys, and that's dangerous. So let me see what Connect Math does, just so I'm consistent. So this will be 4.2. It's probably an assignment, a problem towards the end, I would guess. So let me check out 21. No, 20. What the heck is this? What am I looking at? I should be looking at 4.2. This looks nothing like what we're doing right now. What the heck? That does. What's up with those problems at the end? Okay, sorry. Might need to go alter this. Huh. Okay, it doesn't look like there was a word problem last year. Okay, I'm gonna have to alter this. Okay. All right, so I'm just gonna roll with it. I'll show you both interpretations, okay? So one thing somebody could say if they just took this 0.4 and they said, okay, don't round up, then one possible interpretation could be there were about 115 million people in Mexico. Remember, this is in millions. In, what time is it, you guys? If 4 was what we plugged in, what year?
2014.
Yeah, 2014. Okay, so that could be one possible interpretation. I'm not a big fan of that one because it's losing a lot. It's like its accuracy is like not very good. So another possible interpretation would be, now let me just write out a couple more decimal digits. I had 2 zeros after that. Okay. So 115 million. And we know that there's like 3 here and 3 here. That would be 115 million. Well, that's going to be these digits. 479 would go here. And then 600. Okay, and then after the 0 is a 3. So that would mean 0.3. Okay, so I'd leave it as this number right here. So another interpretation that's better, you guys can see, look at the difference, okay? There were, sorry, about 115, comma, 479, comma, 600 people in Mexico in 2014. So it's just going to depend upon what they end up asking you as far as the rounding. You can see why I like the second one better. Holy cow, we almost lost 500,000 people here with this interpretation, right? It's like, wow, it was really, you know, 500,000 higher than that. So I like this one because it's more accurate, okay? All right. I always like to check. So this one we'll actually go and see if we can Google it. Okay, so let's plug 10 in and let's see how many people we should have expected in Mexico this year from their census. Everybody does the census at the same time. They do it every 10 years. So all countries have done their census, which is kind of tough because of COVID. Some of you probably had people knocking at your door. All right, so we're going to plug in 10. Let's see what happens. Okay, and if I write more decimal digits, okay, we could say, oh, there's around 123 million. That might be what Connect Math wants you to do. Okay, so there were about 123 million people in Mexico in 2020. So they just basically took the 5 and rounded it up. 5 makes this 2 become a 3. I don't like that as much as there were about 122, comma 540, comma 2, 3, and this 9 is going to round the 5 up to a 6. So let me go ahead and put a 6 in here. Now we did have COVID happen, so I wonder if we'll be under that number. It's not a huge amount of people, but it does affect it a little bit. Let's go check and see. Let's Google it. I'm curious. $128, what did we get? Oh, it's close, you guys. We had 120, 123-ish, and it was 128-ish. And this was even an estimate. Here it says, I don't know if everybody's compounded their census data yet or not. Oh, not too shabby. Okay.